My name is Ashley Kane, and this is my presentation of Lab 3 for Physics 2212, and it is the magnetic field of a bar magnet. The intention of this lab is to observe and collect data from the magnetic field of a bar magnet to become familiar with the physics principles of distance dependence, magnetic moment, and the Biot-Savart law. Here are some necessary physics principles to understand for this lab, including the distance dependence and Biot-Savart law, as well as the magnetic field of a dipole. The distance dependence equation is written on the right, and it shows the inverse relationship between magnetic field and distance, because as distance increases, magnetic field decreases, shown in this equation, since n will always be negative. The magnetic field equation on the right also shows this relationship and is based on the magnetic field equation of a dipole, which is represented by the bar magnet in this experiment. We use a phone for measurements in this experiment, so we can assume that the x-axis is along the phone width, y-axis is along the phone height, and z-axis is perpendicular to the phone screen. For the procedure for the physical model, on the left you can see a diagram of the visual component of the physical model. We use a magnetometer app on the phone, which measures the x, y, and z components of the magnetic field at the position of the phone. We would record the x component of these measurements at different locations based on the measurement of the x component of the magnetic field. At these locations, we would measure the distance from the bar magnet and the magnetic field in the x direction. And from these recordings, we produce a graph of the natural log of the distance versus the natural log of the x component of the magnetic field. From this graph and these values, we would calculate the value for distance dependence and the magnetic moment. Here you can see my collected results and graph, as well as the negative relationship shown between the magnetic field in the x direction and the distance from the bar magnet. The graph produced from the previous data results produced the equation y equals negative 2.699x minus 14.126. I then used the distance dependence formula and found that the distance dependence value, n, is equal to negative 2.699, and natural log of k is equal to negative 14.126. Using the magnetic moment equation and the value of natural log of k from the previous distance dependence equation, I found that the magnetic moment from my data to be 3.665 am squared. I then created a GlowScript computational model to represent the same setup as created in the observed model to show the bar magnet and its production of a magnetic field at different locations. I entered constants, including the calculated value for the constant of k in the previous experiment, which was found to be 7.331 times 10 to the negative 7. I then created a function using the values of mu and the distance to calculate the magnetic field at the given location. I then wrote to display arrows on the parallel and perpendicular axis to the bar magnet to represent the magnetic fields at those locations. I used a similar method to calculate the magnetic field at a location 45 degrees from the bar magnet. Here is the visual model produced by the GlowScript computational code. This displays vectors for the magnetic fields at 2 locations in the parallel axis and 4 locations in the perpendicular axis to the bar magnet, as well as displays the calculated vector values. Additionally, at the bottom, there is a calculated value for the magnetic field vector at distance d, 45 degrees from the bar magnet. Here are the differences in magnetic fields observed at 45 degrees from the bar magnet in the observed versus computational model measured in Teslas. There are differences in these values because the computational model only included the magnetic field produced by the bar magnet, which is why there are only components in the x and y direction, whereas the observed model includes magnetic field from the Earth and other magnetic fields, and we can see that there are additional magnetic fields acting in this position because of the non-zero z component. Here are the 2 conclusion questions for this lab. The first question asks for us to consider if we hadn't oriented our experiment to compensate for magnetic north of the Earth. The reason that we did this was to consider the magnetic field of Earth as negligible. Otherwise, there would have been more error and difference between the computational and observed model. The second question asks us to consider what would happen if we were to stick two identical magnets together end to end and run this experiment again. If we did this, the magnetic fields would have increased because of the increased magnetic force from the resulting dipole. The distance would decrease since the magnet is now more powerful.